Hi everyone, welcome to IGCSE Chemistry with the Chemistry Dude. Today we'll be discussing stoichiometry. Your syllabus asks that you're able to define the relative atomic mass. The symbol for the relative atomic mass is AR, A with a subscript R. Now, the relative atomic mass is defined as the mass of naturally occurring isotopes of a substance compared with the mass of carbon-12 atom, which is exactly 12 units. That is, the mass of carbon-12 atom is exactly 12 units. So it's a comparison. You're comparing the mass of the average mass, that is, of naturally occurring isotopes of a particular substance, okay, with the mass of carbon-12. Carbon-12 has got a mass of exactly 12 units. So basically, what you're required to do is to memorize this definition. I would rather you understand it, okay, and understand that by understanding it, I mean that you should understand that is the average mass of an atom of any substance is compared with the standard atom, the mass of the standard atom, which is carbon-12. So carbon-12 is the standard chosen by scientists, okay? And we are required to compare the average mass of every other substance with the mass of carbon-12. Okay, so that's basically all that you need to know regarding relative atomic masses. Relative molecular mass, on the other hand, is calculated by adding the relative atomic masses of all the atoms present in your formula. If it's a molecular formula, all the atoms present in that molecular compound. If it's an ionic compound, then the sum of all the atoms present in that ionic compound. So for example, if we've got carbon dioxide, to find the relative molecular mass of carbon dioxide, you will add the relative atomic mass for carbon, which you will get from your periodic table. So if you look at your periodic table for carbon, you will see that 6 and 12 there. And also for oxygen, you will see 8 there and 16 there. This is what you will see from your periodic table. So you know that the relative atomic mass is the larger of these two numbers associated with the element. So 12 would be the relative atomic mass of carbon and 16 the relative atomic mass of oxygen. So to find the relative molecular mass of this molecule there, carbon dioxide, you add the relative atomic masses and multiplied by the quantities of each of them. So for example, oxygen, you've got 2 oxygens. So there it will be 16 times 2. So let's go ahead and calculate the relative molecular mass of carbon dioxide. So there we've got carbon, we've got 1 carbon, so that would be 12 because the relative atomic mass of carbon is 12, okay? So we say AR as a relative atomic mass of carbon, AR of carbon there, put carbon in brackets, is equal to 12. We got that from our periodic table. And AR for oxygen is equal to 16. We also got that from the periodic table. Therefore, MR of carbon dioxide is equal to 12. That is for my carbon there, plus 16, that is for my oxygen, but I've got 2 oxygens, so I've got to times that by 2, okay? So that would give me 44, yes? So 16 times 2 is 32, 32 plus 12 is 44. So my relative molecular mass for carbon dioxide is 44, okay? It's the addition, the sum of the relative atomic masses of all the elements present in that molecule. Now, if this was an ionic compound, Instead of calling it relative molecular mass, I would have been calling it relative formula mass. But it is calculated in exactly the same way. It is calculated exactly the same way. As an example, if I've got here as a ionic compound, sodium hydroxide, and I want to calculate the relative formula mass for this compound, then I'll go to my periodic table, I'll look up sodium, and I'll see, this is what I'll see associated with sodium. And for oxygen, of course, we looked up oxygen there already, so that's what we'll see for oxygen. And hydrogen would be that, and here would be, that'd be 2, that'd be 1 actually, because the number of neutrons is 0 neutrons. So that's what we'll see for hydrogen. Now to calculate my relative formula mass for sodium hydroxide, Mr, yes, the symbol is the same. So Mr for sodium hydroxide is equal to sodium there, it's 23. Yes, the relative atomic mass of sodium there is 23, plus oxygen, I've got 1 oxygen, so that would be 16 there, that's 16, so 23 plus 16, plus how many hydrogens? I've got 1 hydrogen, so plus 1, so that would be 23 and 10, 33 and 6, 39 and 1, 40. So 40 is my relative formula mass for sodium hydroxide. So for a molecular compound, it's called a relative molecular mass, or you can say for a covalently bonded compound, it's called a relative molecular mass, and for an ionic compound, it is called relative formula mass. Okay, here we've got some worked examples and some boxes for us to work out the relative formula mass and relative atomic masses of these compounds. We've already calculated for carbon dioxide. Now let's take the example here, sulfur dioxide. So sulfur, how many sulfurs do we have? We've got 1 sulfur and we've got 2 oxygens. Okay, so the AR value for sulfur, that's what we need to look up from our periodic table. In your periodic table, you'll find the AR for sulfur, it's 32. This is what in the box that has sulfur in the periodic table. You will see there 16, the atomic number, and 32, the relative atomic mass. So AR is the same as the relative. It is actually the relative atomic mass, so 32. Okay, for oxygen, we did oxygen on the last page, but I'll write it again here. Okay, so oxygen is 8 and 16. So the AR of oxygen, AR for oxygen there, it's 16. Okay, so now we've got our AR value for sulfur there, 32, and AR for oxygen there, 16. We could use those values now to calculate our relative molecular mass of sulfur dioxide. Okay, so because I've only got 1 sulfur, it'll be just 32 plus, I've only got 2 oxygens, so it'll be 2 times 16. Okay, so 2 times 16 is what? 32 as well. Okay, so it'll be 32 plus 32, and that should give me 64 as my relative molecular mass of sulfur dioxide. Let's look at an ionic compound. So the relative formula mass. Calcium chloride. Now, how many calcium atoms do I have here in this compound? I've got 1 calcium atom there and 2 chloride, I should say calcium ion. I've got 1 calcium ion there and 2 chloride ions here, because we're talking about an ionic compound. So of course these will be ions. Okay, so I write it there, 1 calcium ion and 2 chloride ion. Now a calcium ion, the relative atomic mass of a calcium ion is still the same as the relative atomic mass as you would find in the periodic table. So calcium, when you look at your periodic table, you'll see 20 there and 40 there. So the AR of calcium, Ca, is equal to 40. You've got chlorine there as well. When you look at your periodic table for chlorine, you'll see 17 and 35.5. So the AR value for your chlorine there would be 35.5. Okay, so how many calcium do I have? I've got one calcium, so that would be 40 plus 2 chlorines, so it'd be 2 times 35.5, and that should give me what, 40. Okay, so that would be 2 times 35.5 would be 71. Yes, so 40 plus 71 should be 110, 111, isn't it? 111. 111 is my relative formula mass for calcium chloride. Now let's look at another example here. The example of aluminium sulfate. Now I want you to take a minute to write out how many of each atoms do we have here in aluminium sulfate. Okay. Okay, let's go through it now. You should have the number of each atoms written out here in this box. Okay, now let's continue. So aluminium, we've got 2 aluminium. If yours correspond to what I'm writing, then give it a tick. Let me change my ink. I'll use black ink. It's not allowing me to change, is it? Okay, sorry about that. So for aluminium, I've got 2 aluminiums. Okay, and the sulfur here, you can see sulfur is in bracket, and outside the bracket is 3. So I need to multiply this 3 by everything in the bracket. So first I'll multiply it by sulfur to give me the number of sulfur ions I've got here. Okay, now, or sulfur atoms I've got here. So I've got 3 times S is 3, so it's 3S. So I've got 3. So there I've got 3 sulfurs. Okay, so 2 aluminiums, 3 sulfurs. How many oxygen? Well, oxygen, I've got O4 there. So I need to multiply the 4 inside the bracket by the 3 outside the bracket to give me the amount of oxygens that I've got. So 3 4s is 12. So that would be oxygen, would be 12. 12 oxygen. So here we go, 2 aluminiums, 3 sulfurs, and 12 oxygen. So for this, I'll need my calculator to work out my relative formula mass there. Guys, let me, so since we've since we've worked out how much of each atom of the individual elements present in this formula, this ionic compound, now we can use that to calculate the relative formula mass of this compound, aluminium sulfate. So it will be 2 times 27 for aluminium. AR value for aluminium is 27, so 2 times 27 because we've got 2 aluminiums, plus 3 times 32 because sulfur is 32 and we've got 3 sulfurs, okay, plus 12 times 16 because we've got 12 oxygens and the relative atomic mass of oxygen is 16. Okay, so someone do the math there. I'll use my phone to quickly calculate this. And that would give me, oops, this is not quick, is it? So I've got 2 times 27, 2 times 27 plus 3 times 32 plus 12 times 16. And that gives me 342. So my relative formula mass for aluminum sulfate is 342. If you've got that answer, then that's brilliant. Now let's move. Actually, you've got some more boxes here, some blank boxes. Please complete these boxes. Okay, so please calculate the relative atomic, relative molecular mass and relative formula mass of the remaining compounds to complete the box. Reacting masses. So now we'll move on to look at reacting masses. There are two very important laws of chemistry regarding reacting masses. Law number 1, okay, elements always react in a fixed ratio to form a given compound. This is called the law of definite proportion, or sometimes called the law of definite composition. Okay, now let's look at an example of this. Let's say you've got carbon reacting with oxygen to produce carbon dioxide. Now, when carbon reacts with oxygen to produce carbon dioxide, it always do so, these reactants always react in a definite ratio, in a fixed ratio to produce a fixed amount of carbon dioxide. Now, so let's work out what that ratio is, what that fixed ratio or definite proportion is. Now, the AR value for carbon is 12. The AR value for an oxygen atom is 16. So for an oxygen molecule, which contains 2 atoms of oxygen, would be 16 times 2. That will give you 32. Okay, now for carbon dioxide, we've just completed how to calculate the relative molecular mass of a compound. So for carbon dioxide, it would be 12 for carbon plus 2 times 16 for our 2 oxygens. That would give us 44. So the mass of carbon, it's 12 grams, okay? The mass of the molecular or molar mass of oxygen molecule is 32 grams, and the relative molecular mass there of carbon dioxide is 44 grams. Now, to calculate the ratio of reacting masses, we must divide by the smallest of the 3 masses. So we've got 12 grams, 32 grams, and 44 grams. 12 is the smallest of the 3 masses. Okay, so we divide throughout by 12 to calculate our ratio. So 12 by 12 gives us 1. 32 divided by 12 is 2.7. We round it to 2.7. And 44 divided by 12 is rounded to 3.7. So the ratio of reacting masses here, guys, is are 1 to 2.7 to 3.7. Therefore, what mass of oxygen is needed to react with 24 grams of carbon to produce 88 grams of oxygen? Okay, so that's a question for us here. What mass of oxygen is needed to react with 24 grams of carbon? Okay, now to produce 88 grams of oxygen. Well, we can do this mentally quite easily, because we know that 12 grams of carbon produces 32 grams of oxygen. Okay, so if we've got 24 grams of carbon, it stands to reasoning that that represents a double amount. Okay, 2 times 12. So obviously my oxygen will double as well. So that would be 64 oxygen that will be produced. But it's not always that easy to work it out, because this number could have been any number. Okay, the thing is, once you've worked out your the ratio of reacting mass, it doesn't really matter what this number is. It could be a very difficult number to work with. You'll still be able to work it out easily. But here we've got an easy number. Let's use the ratio of reacting mass to work it out. Now, the ratio that we've got there is a 1 to 2.7 to 3.7. Okay, of course, we're talking about here, this is one carbon, that is oxygen molecule, that is, and here it's carbon dioxide. Okay, so it's a 1 to 2.7 to 3.7. Now, I know that whatever amount of carbon I've got here, the amount of oxygen that would need to react with that amount of carbon would have to be 2.7 times more than whatever my carbon is. So it doesn't matter what value I've got here. All I need to do is to multiply that value by 2.7 to find the amount of oxygen that needs to be reacted with it. So 24, excuse me. So 24 grams of carbon will need to react with 24 times 2.7, okay? And that should give me my 64, should give me 64. I'll get my calculator out. So I've got 24 times 2.7 gives me 64.8. So it's roughly what is expected. Roughly what is expected. Because I rounded it off. You see, I rounded it off to 2.7, and that's why my value is a little higher. Okay, but it's close enough for me to say that my value there would be 64. Okay. Now, if I change the amount of carbon there, let's say I random value 15. Okay, so if I've got 15 grams of carbon, again it'll be 15 times 2.7, and it will give me my amount of oxygen. 15 times 2.7 will give me 40.5. 40.5 grams of oxygen. So you see, it doesn't matter as long you work out your ratio of reacting mass, okay? It doesn't matter what amount of any of the reactant you're given, you can find the amount of the other reactant that is needed to react with it to give you your product. Okay, now the second law, law number 2, remember we talked about 2 laws. Okay, we just completed looking at the law of definite proportion. That's what we were talking about all the while. Now we're moving on to law number 2, which states that the total mass does not change during a chemical reaction. So during a chemical reaction, the total mass does not change. What that means is that the mass of your reactant is always equal to the mass of your product. So if I've got 64 grams, which I calculated, of oxygen reacting with my 24 grams of carbon there, then how much carbon dioxide should that be producing? Okay, according to the second rule, yes, according to the second rule, mass is never lost. So mass of reactant, the sum of the mass of my reactants should always equal to the mass of my product. So let's put this to a test. 24 plus 64. So my 64 plus 24 there will give me how much? 88. grams of carbon dioxide. Okay, and this is exactly what I've got there. I've got 88 grams of carbon dioxide produced. So when I react 24 grams of carbon with 64 grams of oxygen molecule, it produces 88 grams of carbon dioxide. These two rules, these two laws, when working with reacting masses, are very important in figuring out the amount in mass of any reactant and product or products produced in a chemical reaction. Now, calculating quantities. Now, let's look at some examples based on what we've just studied, okay? Reacting masses. So example 1 here, and it's only one example. 64 grams of copper reacts with 16 grams of oxygen to give the black compound copper 2 oxide. Copper 2 oxide. I'll remind you of a question that one of you guys posted today regarding formation of copper 2 oxide. But let's finish this first. So now what I want to do here first, very first thing, is to write my equation, write my chemical equation. I'll try my best to squeeze it in here. Okay, so I'll say first step 1, okay, copper reacts with oxygen. So copper has a symbol Cu, plus oxygen is a diatomic molecule, so it's always written as O2, goes to form the black compound copper oxide, CuO. And that's the correct way to write this formula, because copper there has a valence and charge of 2+ and oxygen 2-. So of course, if the valencies are the same, they cancel out each other. So the compound is written exactly like that. Very important that you're able to write your compounds in the correct way before balancing. Okay, moving on. So here we've got 1 copper, so my coppers are fine. My oxygen, I've got 2 oxygens there and 1 oxygen there, so I need to balance my oxygen by adding 2 there. And my copper, now I need to add 2 there in order to balance my copper. So I've got a balanced equation. Now, what did I learn from my question? It said 64 grams of copper reacts with 16 grams of oxygen. Now, the next step here is for me to write the AR values for my, actually, I don't need to write the AR values. Now, what I can go ahead and do is write the reacting masses. So for copper, it's 64 grams. And for oxygen, so it's reacting with 16 grams of oxygen. Okay, so based on law number 2, which states that the mass of the reactants, the combined mass of reactants is always equal to the mass of my product. So I can go ahead and write the mass of my product here, even though it wasn't given. Okay, so 16 plus 64 will give me 80 grams of copper oxide. Does everyone understand how we got that? Again, I add the masses of my reactants in accordance with the second law, which states that mass is always conserved during a chemical reaction. Mass is never lost. Therefore, the mass of my reactants will, the sum of the mass of my reactants will always equal to the mass of my product. Okay, so now that I've got my reacting masses, the next step, so that's step number 2, if you like. So step number 2 there. Step number 3 would be to find my ratio of reacting masses by dividing by the smallest of the masses, which is 16. So therefore, I'll have here 64 divided by 16, 16 divided by 16, and 80 divided by 16. And this should give me my ratio there of 4 to 1 to 5. You can calculate it. So I've calculated my ratio. Now that I know my ratio, I'm ready to deal with any amounts of any of my reactants, okay, to find the amount of the other. Okay, so let's go ahead. The first question 8 says, what mass of copper will react with 32 grams of oxygen? So they've given me oxygen. This is my oxygen there. This is my ratio of oxygen is 1 oxygen to 4 copper. So if I've got 32 grams of oxygen, I know my copper is 4 times that. So I will calculate the amount of copper that will be needed to react with 32 grams of oxygen by multiplying 32 by 4. Okay, so that would give me 32 times 4, that would be 128. Okay, so therefore, the amount of copper that is required to react with 32 grams of oxygen, okay, is 128 grams of copper. Again, how did I calculate that? I know that my reacting mass, the ratio of reacting mass between copper and oxygen is 4 to 1. 4 copper to 1 oxygen, which means that if I've been given 32 grams of oxygen and asked what mass of copper is needed to react with it, all I need to do is to multiply 32 by 4, okay? And that will give me 128 grams of copper. Next question, B, what mass of oxygen will react with 32 grams of copper? So now I've got 32 grams of copper here. Again, my ratio is 4 to 1, 4 copper to 1 oxygen. Now, if I've got 4 copper, it will need to react with 1 oxygen. So what about if I've got, let's say, 8, let's say I've got 8 grams of copper there. How much oxygen would it need to react with? It will double it, isn't it? It will be 2. So if 4 to 1, then 8 grams of copper, 8 grams of copper will need to react with 2 grams of oxygen. Yes, and then if I've got 12 grams of copper, yes, 12 grams will need to react with 3 grams of oxygen. You can see the pattern there, isn't it? Yes, I'm going up. If I go up by 4, here I go up by 1. Yes, so the next step is 16 grams. So 16 grams of copper will have to react with 4 grams of oxygen. Now 16 is half of 32. So stands to reason if 16 grams is needs to react with 4 grams of oxygen, then 32 grams of copper will have to react with 8 grams of oxygen. So I can work it out this way, but that's a long way. I can do this a lot faster. All I need to do is look at the number, the mass of my copper that I've got, and it's 32 grams of copper, and divide it by the ratio of copper in the ratio of reacting masses. What's my ratio of copper? Is 4. So 32 divided by 4 will give me the amount of oxygen there. Yes, and that would be 8. So I don't need to do all of that. All I need to do is to look at the mass that I've got there, and it's the mass for what? It's the mass for copper. So I look at the ratio of copper in my molar, in my ratio of reacting masses, and I can see that my ratio of copper is 4. Okay, so I divide 32 by 4, and that gives me 8. Okay, so my answer there would be 8. Now, what mass of copper oxide, excuse me, what mass of copper oxide will be formed in B? Now, this is quite simple. We use the second rule, the second law, which states that the sum of the masses of your reactants should give you the mass of your product. So I know that in B, I reacted 32 grams of copper with 8 grams of oxygen. So 32 grams of copper. Okay, that's it there. Cu plus oxygen there. It was 8 grams. So I know what mass of copper 2 oxide. My copper oxide there will be 32 plus 8. That would be 40 grams, because mass is always conserved. The sum of the masses of your reactants will always give you the mass of your product. So what mass of copper 2 oxide will be formed in B? The answer there would be 40 grams. 40 grams. Okay, moving on to section D. How much copper and oxygen will give 8 grams of copper oxide? Again, I look at my ratio of reacting masses, okay? And I can see that that 8 grams is 8 grams of copper oxide. So if I want to know how much oxygen will need to react to produce 8 grams of copper oxide, I divide my 8 grams there by the ratio of copper oxide in my ratio of reacting masses. So if my ratio is 4:1:5, 5 representing my copper oxide, so I divide 8 by 5, and that should give me 1.6. 1.6. So 1.6 there is the amount of oxygen. Because my copper oxide is 5 times more my oxygen. Okay, if I want to double check to make sure that this is correct, I can multiply 1.6 by 5 and I'll get 8. So that's the way to double check that my answer is correct. So 1.6 is the amount of oxygen that I need to react to produce 8 grams of copper oxide. So let's write my equation here. Cu plus O2 goes to form CuO. Now, I know that I need to react 1.6 grams of oxygen to produce 8 grams of copper oxide. But what I don't know is how much copper is needed. Now, it's using the second law. If I know my product, mass of product, and mass of one of the reactants, all I need to do is to minus 1.6 from 8 to give me the mass of my other reactant, which would be 6.4. Okay, so 8 minus 8 grams minus 1.6 grams is equal to 6.4 grams. So my mass of copper that is needed is, mass of copper there is 6.4. 6.4 grams of copper is needed to react with 1.6 grams of oxygen molecule to produce 8 grams of copper oxide. So my answer there for D would be copper 6.4 grams and oxygen molecule, it's 1.6 grams. Those two needs to react to produce my 8 grams of copper oxide. And to double check, I can add 6.4 plus 1.6, and that should give me my 8 grams there. Okay, so that's all regarding this problem. Now let's move on to look at the mole concept. the mole concept. Now, what is a mole? What is a mole? What exactly is a mole? A mole is a collection of a very large number of particles. A collection of a very large number of particles is called a mole. Okay, this large number of particles, we refer to it as Avogadro constant. Avogadro's constant. Okay, and the amount of particles that are present in Avogadro's constant is 6.02 times 10 to the 23 particles. So this is the amount of particles present in Avogadro's constant. Therefore, one mole of any substance will contain this number of particles. 1 mole of any substance will contain 6.02 times 10 to the 23 number of particles. Okay? Now, therefore, if we were to take an element, carbon, yes, 1 mole of carbon 12, the isotope of carbon, carbon 12, the most abundant isotope of carbon, okay, 1 mole of carbon 12, which has a mass of exactly 12 units, okay, which have a mass of exactly 12 atomic mass units, okay, will contain 6.02 times 10 to the 23 atoms of carbon 12. Okay, 1 mole of carbon 12 will contain 6.02 times 10 to the 23 atoms of carbon 12. The mass of 1 mole of carbon 12 is exactly 12 grams or 12 units. Oh, sorry, I said 1 mole, so it must be 12 grams, and I'll explain why in a minute. So the mass of 1 mole of carbon 12 is exactly 12 grams. And we refer to the mass of 1 mole of carbon 12 as the molar mass of carbon 12. It's the MOLAR, molar mass, okay, of carbon 12. And it has a value, a symbol, MR. So you got to be careful because relative molecular mass has the same symbol and relative formula mass has the same symbol. But the mass of 1 mole also has that same symbol. So the mass of 1 mole of carbon 12 is 12 grams. Okay, so molar mass of carbon 12 is equal to 12 grams. Now the molar mass of any element in the periodic table, like carbon 12 here, you would notice that when you check your periodic table, the relative atomic mass of carbon is exactly 12, or rounded off to 12. Okay, so the relative atomic mass of carbon is the same as the molar mass of carbon, 12 grams. So we want to make a statement that works all the time, always works. The molar mass of any element in the periodic table is the relative atomic mass of that element in grams. Again, the molar mass of any element in your periodic table is the relative atomic mass in grams. So we can choose any element, you name it. If we choose iron, Fe, check up the relative atomic mass of iron, it's 56, 55 point something something. We round it off for simplicity. So that's 56. So the molar mass of iron would be 56 grams. Okay. Now, what about the relative, the molar mass of a compound? The molar mass of a compound. Okay, we worked out already that the molar mass of an element is the same as its relative atomic mass in grams. What about the molar mass of a compound? Well, the molar mass, another statement, the molar mass of a compound is the molecular mass of that compound in grams. The molecular mass of that compound in grams. So let's take water, for example. Water is H2O, H2O. Now, what is the relative molecular mass of water? How do we find it? We add the relative atomic masses of each atoms. So hydrogen, there is 1, and we've got 2 of it, so 1 times 2 plus 16 for oxygen, that gives us 18. So the relative molecular mass of water is 18. Okay, now what is the what is the molar mass of water? Molar mass of water is the relative molecular mass of water in grams. So for water, molar mass is equal to 18 grams. So just to summarize, the relative atomic mass of any element in the periodic table is used to calculate the molar mass of that element in grams. Again, the molar mass of any element in the periodic table is the same as its relative atomic mass in grams. The molar mass of any compound, molecular compound, is the relative molecular mass of that compound in grams. Okay, now, how much particles does 1 mole of any substance consist of? It consists of Avogadro's number of particles, which is 6.02 times 10 to the 23. And it doesn't matter. These particles, if it's water, so water, H2O, is made up of water molecules. So 1 mole of water will have 6.02 times 10 to the 23 water molecules. Okay, if it's hydrogen, okay, hydrogen, H2, its molecule, 1 mole of hydrogen molecule will have 6.02 times 10 to the 23 molecules of hydrogen. Okay, let's see then, what about copper? 1 mole of copper will have 6.02 times 10 to the 23 atoms of copper, because copper is a metal and it's made up of atoms. Okay, so let's move on. Now calculating mass from moles. Now 1 mole of helium, okay, symbol of helium is He. It's a noble gas. Okay, the relative atomic mass of helium, there, when you look at your periodic table, you will find that it's 4. Now, the relative molecular mass of helium, well, helium is not a molecule. Okay, not a molecule. It's an atom, not a molecule. Okay, so it doesn't have a relative molecular mass. Okay, so what is the mass of helium? How do you find out the mass? Now, mass is found by multiplying the number of moles by the relative atomic mass of that substance. So mass there is equal to moles times the AR value there. So number of moles is 1 mole there. So mass of helium is equal to 1 times the relative atomic mass, which is 4, which gives us 4 grams. That's how we calculate the mass there. The mass of helium is 4 grams. Now, 2 moles of oxygen. 2 moles of oxygen. Now look at this. 2 moles of oxygen, okay, molecule. Okay, we've got oxygen there, it's a molecule. So 2 moles of oxygen molecules. Now, the AR value of an oxygen atom is 16. Okay, AR value of oxygen atom is 16. But we're asked to find out the mass of 2 moles of oxygen molecule. So this is what we do. 1 mole of oxygen molecule consists of 2 atoms. So that would be, I'll calculate my relative molecular mass there. So it will be 2 times 16. That would give me 32. Okay, that is 32. That's for 1 mole of oxygen molecule, just that. But what if we've got 2 moles of it? 2 moles of oxygen. Okay, so 2 moles of oxygen molecule will be that O2 twice. Yes, because it's 2 moles of oxygen molecule. And perhaps I should write molecule here. Okay, so 2 moles of oxygen molecule. So we got 1 mole of oxygen, 1 oxygen molecule there, and another oxygen molecule there. So 1 mole of oxygen molecule is 32 grams. Therefore, 2 moles of it would give me 32 times 2. Okay, that is to accommodate for this one. So that one is 16 times 2 gives me 32, and this one would be the same as well. 16 times 2 should equal to 32. So altogether, 2 moles of oxygen molecule will be 64. Okay, so what mass of oxygen molecule? What mass do we have there? The mass there would be, we've calculated the mass already. Perhaps I shouldn't have done this because I skipped a few steps. So what I'll do, I'll go back over those steps. I should have left this step for last. Okay, I should have used the number of moles last. So what I'll do here, I will go back, okay, in order to make this step clear. Now, 1 molecule of oxygen has got 2 atoms of oxygen. Okay, so that would give me 32 for my relative molecular mass of oxygen. That would be 32. Now, I've got how many moles of oxygen? I've got 2 moles of oxygen there. Okay, so to find my mass of oxygen, mass is equal to moles, which is 2 times the molecular mass, relative molecular mass of oxygen is 32. Okay, so 2 times 32 equals 64. Yes, this would be the step-by-step way to work it out. Okay, I shouldn't have worked it out. I shouldn't have taken shortcuts, basically. So again, just to clarify here, we've got 2 moles of oxygen molecule. Okay, 1 mole of one oxygen molecule consists of 2 atoms of oxygen. The relative atomic mass of 1 oxygen atom is 16, but since you've got 2 oxygen atoms, the relative molecular mass will be 2 times 16, which would be 32. Now I've got my relative molecular mass. Now I want to find my mass. Mass is equal to moles times relative molecular mass, because oxygen is a molecule there. Okay, so it'd be number of moles would be 2. We are given that, and we've calculated our relative molecular mass there. It's 32. So mass is equal to moles times relative molecular mass. So 2 times 32 gives us 64. Now, I would like you to work out, take a minute, pause your video, work out the mass of ethanol, the mass of 1 mole of ethanol. Work out the mass of 1 mole of ethanol. Once you finish, unpause and continue. Now, the mass of 1 mole of ethanol would be carbon. You've got 2 carbons there, so 12 times 2, 12 times 2 is equal 24. Hydrogens, you've got 5, so 5, 1 times 5, that is 5. And oxygen, you've got 1 oxygen there. Actually, hydrogen, you've got 6, 5 plus 1, that is 6 hydrogen. So it's 1 times 6, so that is 6 there. Okay, and oxygen, you've got 1 oxygen, so that is 16 times 1, and that is going to be 16. So now the relative molecular mass there of this compound would be 24 plus 6, that is 30, and 30 and 10, 40, 40 and 6, 46. Yes, so 46 is my relative molecular mass of this compound, ethanol. Now, I want to find the mass of 1 mole of ethanol. Mass is equal to moles times, in this case, it'll be relative molecular mass, or what is called molar mass, the mass of 1 mole. So that would be 1 is the number of moles times 46, okay, which will equal to exactly 46 grams. So if this is your answer, you can give yourself a tick. Now calculating moles. Calculating moles. How do we calculate moles? To calculate moles, we use the equation moles is equal to mass over molar mass. Remember, we said the molar mass of an element in the periodic table is the same as the relative atomic mass of that element. If it's a compound, then it is the same as the relative molecular mass of that compound. Okay, so the molar mass is the same as the relative atomic mass or the relative molecular mass of a compound. Now we can rearrange this equation using a triangle to find any of the quantities there, to find mass. Mass is mostly what we'll be required to calculate. Okay, so we can use a triangle to rearrange the equation to find mass. So mass in this case would be equal to moles times molar mass. Okay, moles is given here, moles is equal to mass over molar mass. Now let's look at some examples. It says here, exercise 1, calculate the mass of 0.5 moles of bromine atoms. Now, so we're asked to calculate the mass. So that's the first thing. So we write the equation, making mass the subject of the equation, of the formula. Mass there is equal to moles times molar mass. The number of moles is given 0.5. The molar mass of bromine atom, we can get it from our periodic table, okay? And that would be 80. For bromine, it'll be 80. So that would be 80 times 0.5. What's your answer? 80 times 0.5, that would be 40 grams. That'd be 40 grams. Okay. Now let's move on to question number 2. Question number 2, calculate the mass of 0.5 moles of bromine molecule. So now we've got here bromine molecule, not a bromine atom. So we'll talk about that in a minute. Now, again, the equation we're asked to calculate mass. So we know we're using the formula mass is equal to moles times molar mass. Okay, now we've been given our moles, which is 0.5 times 0.5 times the molar mass, but this is a bromine molecule. So this Br2, not Br, bromine atom, not Br, it's Br2. So here my relative molecular mass of the bromine molecule will give me the molar mass of bromine molecule, which would be, if a bromine atom has a mass of 80 units, or a molar mass of 80 grams, then a bromine molecule will have a mass of 80 times 2, which is 160 grams, which is 160 grams. So for a bromine molecule, the relative, the molar mass would be the same as the relative molecular mass, which would be 160 grams. So my answer there would be 80, yes, would be 80 grams. My mass there would be 80. Okay, so calculate the mass of 0.5 moles of bromine molecule. It will be 80 grams. 80 grams. Okay, question number 3. How many moles of oxygen molecules are in 64 grams of oxygen? So here you're asked to calculate the number of moles. So then we use the equation in its original form. Moles is equal to mass divided by molar mass. So we've got the mass of oxygen is 64 grams, and the molar mass of oxygen is what? The molar mass of oxygen molecule, guys, not oxygen atom. Okay, oxygen molecule, and the oxygen molecule has a molar mass which is equivalent to its relative molecular mass. Oxygen molecule is O2. Okay, so it would be the relative atomic mass of oxygen is 16, but here it will, because it's a molecule and not an atom, okay, it's 16 times 2, which is 32. So that would be divided by 32, which will give us how many moles? 2 moles. Give us 2 moles. So 64 there divided by 32 is equal to 2 moles. Moles and equation. Moles and equation. The equation for the reaction of carbon and oxygen is as follows. Carbon plus oxygen, okay, oxygen is written in its natural state, O2, so diatomic molecule produces carbon dioxide. Carbon plus oxygen produces carbon dioxide. Now, what can we tell from the above formula, from the above equation? Well, we can tell the amount of each atoms of carbon and oxygen reacting to produce carbon dioxide. And we can write that. We can say that one carbon atom reacts with one oxygen molecule to form one carbon dioxide molecule. Okay? But we can also write the amounts in terms of moles. We can write amounts in terms of moles from the equation as well. From the equation, we can see that 1 mole of carbon, and we know it's 1 mole because nothing is written here. it's as if there is an imaginary one there. When nothing is there, it's as if it's an imaginary one. So 1 mole of carbon reacts with 1 mole of oxygen molecule to produce 1 mole of carbon dioxide molecule. Yes? Now, moles can be converted to mass. Moles can be converted to mass quite easily by using the equation that we looked at on the previous page. Okay, mass is equal to moles times molar mass. And the molar mass is the same as the relative atomic masses. Okay, if the number of moles that you've got is 1, then your mass is always going to be the same as the relative atomic mass. Okay, so for carbon, the number of mass is going to be 12 because the relative atomic mass of carbon is 12. So molar mass of carbon is 12 grams. Okay, so the mass of carbon is going to be 12 grams. So if the number of moles is 1, then you don't really need to use the equation. You can just choose the relative atomic mass of the element or relative molecular mass of the molecule and add grams to it. It's that simple. That's if the number of moles is 1. Okay, so moles can be converted to mass since 1 mole of any substance is its relative atomic mass expressed in grams. So for carbon, for 1 mole of carbon, the mass of carbon will be 12 grams. So 12 grams of carbon will react with 32 grams of oxygen to produce 44 grams of carbon dioxide. Yes, all we've done here, because the number of moles is 1 mole of each of those, which we deduce from our formula. Like I said, if nothing is written in front there, it's an imaginary 1. Okay, so 1 mole of carbon is 12 grams of carbon. It's its relative atomic mass in grams. 1 mole of oxygen molecule is 32 grams of oxygen molecule. And 1 mole of carbon dioxide molecule is 44 grams. Okay, and that is given by 12 for carbon plus 16 times 2 for oxygen. That gives us 32. So that's how we got to that gives us 44. Okay, so that's how we got to these masses. Now, of course, if the number of moles are different, then you'll have to use the equation to calculate your mass. Okay, but by going to the periodic table and finding the molar mass, which is the same as the relative atomic mass for elements, or relative molecular mass for molecules, okay, and use that to calculate your mass. Now, if you've understood that well, then let's work out this problem below, okay? Since substances always react in a definite ratio, according to the law of definite proportion or equal composition, okay, 6 grams of carbon will react with how many grams of oxygen to produce how much grams of carbon dioxide. Okay, first of all I need to do is to look at my masses there and work out my ratio of reacting masses. Okay, I can work out my ratio of reacting masses quite easily from these masses to determine how much mass of oxygen and carbon dioxide is needed to react with 6 grams of carbon. And this is done quite simply by dividing by the smallest of the 3 reacting masses. So that is 12 divided by 12. That would be 1, and then I've got 32 divided by 12. That would be what? 32 divided by 12. Let me work that out quickly. My mental math is not working at the moment, so I'm using my calculator. 32 divided by 12. That is 2.6. 2.6. And 44 divided by 12, that would work out to be 3.6, recurring as well. I can easily round these both off to 7, 2.7 and 3.7. Okay, so this is my ratio of reacting mass. So if I've got 6 grams of carbon, the amount of oxygen that is needed to react with that would be 2.7 times more. Okay, so 2.7 times 6, 2.7 times 6 would give me what? 2.7 times, clear, 2.7 times 6 is 16. 16, so the amount of oxygen would be 16 grams of oxygen. Now, I don't need to go to my ratio of reacting masses to work out the amount of carbon dioxide. I can just use the law number 2, which states that mass is always conserved. So if I've got 16 grams of oxygen and 6 grams of carbon, okay, then I know that the amount of carbon dioxide that would be produced would be 16 plus 6. And 16 plus 6 would give me 22 grams of carbon dioxide. I can also work it out from the equation, okay, because I know the amount of carbon dioxide produced would be 3.7 times more than my carbon. So if I've got 6 grams of carbon, all I need to do is to multiply 6 by 3.7, and I should get my 22. So there you go, 3.7 times 6 gives me 22. So both ways work. I can use the first law of definite proportion to work out the amount of carbon dioxide, or I can use the second law, which states that mass is always conserved, to work out the amount of carbon dioxide that is produced. How to calculate masses from equations. So how can we use equations to calculate mass? These are the steps. Write a balanced equation for the reaction. This will show the number of moles present, the number of moles of each reactant, and the product present. Secondly, write the AR or MR values for reactants and products. Remember, your AR values are taken from your periodic table. Your MR value is the sum of the AR values of the atoms present in your compound. 3, multiply the number of moles of each substance by its AR or MR value to give the number of mass. Using the equation, mass is equal to moles times AR value. That's if it's an element. Okay, but if it's a molecule, if it's a compound, then it would be moles times the MR value, which is the same as both of these, but it's MR or AR, it gives you the molar mass, which has, ironically, has got the same symbol as the MR. Okay, once you find the theoretical mass, that is the maximum mass that you can potentially produce, okay, from the equation, you can go ahead to calculate the actual mass from the amount of the reactant that has been given. Okay, now let's look at a practical example of this. Now, example, hydrogen burns in oxygen to form water. What mass of oxygen is needed for 2 grams of hydrogen, okay, mass of water is, what mass of water is produced? Yes, okay, and what mass of water is produced. So first of all, I take clues from my question to write my balance equation. Okay, I know that hydrogen burns in oxygen, so it's a reaction between hydrogen and oxygen. It's a combustion reaction. Okay, so hydrogen, H2, before balancing my equation, I write it out like this: H2 plus O2, because they're both diatomic molecules, goes to produce H2O. That's my formula for water. Okay, now I need to balance my equation. My oxygens are obviously not balanced. So I've got 2 oxygens there, so I need to put 2 there to balance my oxygen. That gives me 4 hydrogen on my product side, so I need to put 2 there to balance up my hydrogen. Now my equation is balanced, and that's why it's written like this. Now what can I ascertain from this equation? Well, I can tell that 2 moles of hydrogen molecule is reacting with 1 mole of oxygen molecule to produce 2 moles of water molecules. And that's what I've written there. 2 moles of hydrogen molecule react with 1 mole of oxygen molecule to produce 2 moles of water molecules. Now, I can calculate the mass of each of these substances by multiplying the number of moles by the molar mass. That is using the equation, mass is equal to moles times molar mass. So molar mass has got the symbol MR, okay? And it's given by taking the relative atomic mass or relative molecular mass and placing the gram sign next to it. So here we go. 1 molecule of hydrogen has got a mass of 2 grams, because a molecule of hydrogen consists of 2 hydrogen atoms. Okay, so it's a molecule of hydrogen, that's it. 2 atoms of hydrogen bonded together covalently. So each of them has a relative atomic mass of 1. So 1 plus 1 gives me 2 grams. 2 grams therefore the molar mass of hydrogen. For oxygen, again, oxygen molecule, 1 mole of oxygen molecule has a mass of 32 grams. And how does that work? Well, oxygen molecule consists of 2 oxygen atoms, double bonded. Each of them has a relative atomic mass of 16. So 16 plus 16 gives you 32. Okay. Now, water, my relative atomic masses of hydrogen and oxygen there. Hydrogen, it's we've got 2 hydrogens, so it's 2, and oxygen is 16, so that is 16 plus 2 gives me 18. Okay, now I need to use these relative atomic masses to calculate the calculate the mass of my substances. So that is given by multiplying the number of moles by the molar mass. Molar mass of hydrogen is 2 grams. Number of moles of hydrogen is 2. So 2 times 2 gives me a mass of 4. So mass of hydrogen is 4. Mass of oxygen is exactly 32 because you've got 1 mole of oxygen. So 1 times 32 gives you 32. The molar mass of water is 18. And I've got 2 moles of water. So 2 times 18 gives me 36 grams of water. Now, next step is to find my ratio of reacting masses. So my ratio of reacting masses are 4 divided by 4. Of course, I divide by the smallest of the 3 reacting masses. So 4 divided by 4 is 1, 32 divided by 4 is 8, and 36 divided by 4 it's 9. Okay, so that's why the ratio of reacting mass, 1 to 8 to 9. Now let's go back to my question. It says, what mass of oxygen is needed for 2 grams of hydrogen? So I've got an amount there, and I need to know how much oxygen will react with this amount. my 2 grams of hydrogen. I know that whatever my hydrogen is, the amount of hydrogen that I've got, whatever it is, my oxygen is always going to be 8 times that amount. 8 times that amount, because the ratio is 1 to 8. So when I've got 2 grams of oxygen, okay, the amount of, 2 grams of hydrogen, the amount of oxygen that is needed to react with that 2 grams of hydrogen would be 2 times 8. Yes, because my oxygen is always going to be 8 times whatever my hydrogen is. So when my hydrogen is 1, my oxygen is 8. When my hydrogen is 2, my oxygen will be 16. So that's why I've got 16 grams there, okay, of oxygen molecule. Okay, and what mass of water is produced? Well, I look at my ratio of reacting masses again. I know that whatever my hydrogen is, my water will always be 9 times it. So what is 9 times 2? Because my hydrogen is 2 grams. So 9 times 2 will be 18. So that's why I've got 18 grams of water being produced there. Okay, now let's look at a practice problem here. The reaction between magnesium and oxygen is as follows. 2 moles of magnesium react with 1 mole of oxygen molecule to produce 2 moles of magnesium oxide. Okay, now how many moles of magnesium atoms reacts with 1 mole of oxygen molecule? You can look at your equation and figure that out. I've got 2 moles of magnesium atom there. So the answer for A is 2. Okay, 2 moles of magnesium atoms react with 1 mole of oxygen molecule to produce 2 moles of magnesium oxide. Remember, the number written at the coefficient gives you the number of moles. If nothing is there, as in the case of oxygen here, then it is 1 mole of oxygen molecule. So that's a molecule of oxygen. Okay, B, the AR values for magnesium and oxygen are magnesium 24 and oxygen 16. Now, how many grams of oxygen reacts with 64, 48, and 12 grams of magnesium? So let's work out our, first of all, we need to find our ratio of reacting masses. Okay, so how do we find our masses? We first calculate our mass from the equation. Mass is equal to moles times molar mass. Okay, so let's write our equation again here. Mg plus O2 goes to form MgO. So that's how my equation is written before balancing. Everything is written in the way it exists in nature. So now I need to balance my equation. My oxygen is not balanced there, so I need to put 2 there. And this means that I've got to put 2 there to balance my magnesium. So now my equation is balanced. And what that tells me is that I've got 2 moles of magnesium reacting with 1 mole of oxygen molecule to produce 2 moles of magnesium oxide. So I've got the number of moles. I've got my number of moles of each substance there in my reactants and my products. Now I need to find the relative atomic mass of each of these, or relative molecular mass, which will allow me to calculate my molar mass. So the AR for magnesium, AR value of magnesium is 24, okay? And the MR value for oxygen molecule there is 32, okay? Because it's 16 times 2 there, yes? Give me 32. And of course, the MR value for magnesium oxide, so MgO, is equal to 2 times 24, 2 times 24 plus 2 times 16, 16 times 2. So 24 and 24, that's 48, plus 16 and 16, 32. So that would give me what? 8 and 4 is 10, so 0. That gives me 80, isn't it? 4 and 3, 7 and 1, 8. So that gives me 80 there. Okay, so my MR value, my molar masses for each of these will be molar mass, MR for molar mass for magnesium is 24 grams. Molar mass for oxygen, molar mass for oxygen molecule is 32 grams. And molar mass for my magnesium oxide, MgO, is equal to 80 grams. Okay, remember, molar mass is the same as the relative atomic mass or the relative molecular mass, except that when we write the molar mass, we write it with grams next to it. So I've got two most important things that I need here. I've got my moles for each of them, and I've got my molar mass for each of them. So I can use those two to calculate the masses. So mass for magnesium is equal to 2 times 24. Okay, and that should be 48, equals 48 grams. Mass of oxygen, well, is moles, which is 1. So mass of oxygen is equal to 1 times 32, which is 32 grams. And mass of magnesium oxide would be 2. What have I done here? I've made a mistake here. So what I've got here, I've calculated the mass here already of magnesium oxide. Yes, this is shortcuts. Okay, let me go back and recalculate this so that I can use the steps. Okay, I don't want to confuse you by taking shortcuts. So let me make use of the steps here. Okay, so what we've got here is 2 moles of magnesium oxide, but the relative molecular mass of magnesium oxide, there would be magnesium, it's 24, plus oxygen, you've got 1 oxygen there, plus 16. Okay, so 24 plus 16 would give me 40, isn't it? Would give me 40. So to calculate the molecular mass, so the molar mass of magnesium oxide would be the same as its relative molecular mass in grams. So that would be 40 there. Let me use my eraser. So that would be 40 grams. Now, you'll see why I had 80 there before. Now, when I calculate my mass of magnesium oxide now, I've got 2 moles of magnesium oxide there. So it would be 2 times 40, okay? And that would give me 80 grams, okay, of magnesium oxide. So that's why I had 80. I took shortcuts, which is not good when you're teaching. Okay, so now that I've got my reacting masses, okay, the mass of my reactants and masses of reactants and products, I can find my ratio okay, of reacting masses by dividing by the smallest of the lot. So dividing by 32, yes, dividing by 32 there and by 32 there, because 32 is the smallest. That would give me a ratio of, again, let me get my calculator out. So it would be 48 divided by 32, and that would be 1.5. So that would be the 1.5. Okay, 1.5 to 1, and this would be 80 divided by 32. 80 divided by 32 is 2.5. 2.5. So the ratio is 1.5, okay, to 1 to 2.5. So that's my ratio of reacting masses. So I'll come to this side to complete. I'll move over to this side here. Where's my pen? Oh, here we are. So my ratio, let me write it here again, 1.5 magnesium. So magnesium there, it's 1.5. Then I've got oxygen molecule is 1. And then I've got my magnesium oxide there, it's 2.5. So my ratio, again, 1.5 to 1 to 2.5. Now I can tackle my problems because I know my ratio of reacting masses, so I can find out the amount of any of my reactants or product that is needed once I'm given the mass of one of the reactants or the mass of my product. Okay, so in this case, we're given the mass of magnesium in all three cases. So when 64 grams of magnesium reacts with oxygen, okay, what mass of oxygen does it need to react with? What mass does 64 grams of magnesium, what mass of oxygen does 64 grams of magnesium need to react with to produce magnesium oxide? Now I know that whatever the number of magnesium is, okay, to find the amount of oxygen that it reacts with, I'll have to divide it by the amount of magnesium in the ratio. Okay, so I'm given magnesium there. So I locate magnesium in my ratio, it's here, 1.5. So the ratio of magnesium to the others is 1.5. So I divide 64 by 1.5. Okay, to find out the amount of oxygen that is required to react with 64 grams of magnesium, I divide 64 grams by 1.5. Okay, that would give me 64 divided by 1.5 is 42 grams, 42.6. So we can round that off to 43. So again, 64 divided by 1.5 is equal to 43. So what that is saying to me is that 64 grams of magnesium will need to react with 43 grams of oxygen. Okay, we'll need to react with 43 grams of oxygen. Now, how much oxygen will 48 grams of magnesium need to react with? Again, you do the same. 48 divided by 1.5. 48 divided by 1.5. And that should give you 32 grams. So 48 grams of magnesium will need to react with 32 grams of oxygen. Okay, and how about how much oxygen will 12 grams of magnesium need to react with? Again, 12 divided by our 1.5 there. Okay, and that will give us 12 divided by 1.5. That would be 8. That would give us 8 grams. So when we react 64 grams of magnesium, okay, The amount of oxygen that would need to react with that to give us magnesium oxide would be 43 grams. Okay, the amount of oxygen that would need to react with 48 grams of magnesium will be 32 grams of oxygen. And the amount of oxygen that would be needed to react with 12 grams of magnesium would be 8 grams of oxygen. Okay, the next topic we want to move on to is